Sulfur is a slow-release mineral in elemental form. It requires microbial activity to turn it into sulfate, which a plant can use. So again, that's historically what we've had that have produced our slow-release sources. Those of you who use a lot of organic materials know that over time that your soils will be releasing more nutrients because of the mineralization from past organic material. All right, moving on to an older technology that's still being used, the urea aldehyde products, where urea is reacted with different types of aldehydes to give us different products, like the urea formaldehyde products, methylene urea products, triazone products, and then IBDU. According to the length of the chain that's produced in this reaction will determine how slow release they are. These are used extensively in the turf industry, which we'll talk about here in a little bit. But again, it's an old technology, depends on the length of the chain. One thing is, though, it can be made into solid or liquid forms. And so one area that you do see this being used quite a bit is in liquid fertilizer formulations to provide nitrogen. You need microbial activity or activity of a plant to release the nitrogen. The exception would be the IBDU, which is releases by hydrolysis or interaction with water, so it's the size of the granule. Did some research on IBDU back in the early 80s in vegetable crops, great nitrogen source, and as long as you you're doing a even watering job, say under drip irrigation under plastic, you can have a pretty good release pattern. Problem is it costs too much. And we could never get it economically to give us the benefits that we needed. So these are materials that are out there through this, and that's what happens is the longer chain formaldehyde, urea formaldehyde gets acted on by microbes and it releases urea. It works very well. It's used extensively in the turf industry. And you can see there the two urea formaldehyde products are giving more good response, in this case Bermuda grass, over time compared to the fertilizer control. Where we probably have a fit in this room is the use as a liquid product, liquid solutions. These have been sold for use in field crops. As a overall liquid source of nitrogen for slow release, what research that has been done in the region hasn't really been that promising in crops like corn. So it's not really reducing our need for side dressing. It's not giving us an extra yield benefit. Where it has had a fit is as a foliar fertilizer to provide nitrogen. The methylene ureas, triazone, those products have a lower, they don't have a lower phytotoxicity possibility. So they do not burn the leaves as much as straight nitrogen solutions. So you can apply these usually in a mixture with the standard soluble nitrogen, but you have less potential for burning your plants. So they are readily absorbed through the cuticle of the leaf. They are transported, maybe react a little differently in the plant than say our standard nitrate or ammonium forms that go through the leaf as a foliar. And really they enter the leaf about the same as the other soluble nitrogen products, but some of the research I've seen showing that they're ending up a little bit different places in the plant, but they are effective as a foliar nitrogen source. So I think a number of you in this room probably have used these or sell these products, so that's probably the best fit that they do have here in the Midland. All right, so those are the old technologies. We'll move on to the newer technologies, and when I say new, that means at least 40 years ago or younger. So coatings have been around for a long time. We have mineral coatings that have been put around, fertilizer particles, fatty acids, laxatives, and paraffin. Any of you ever bought bagged calcium nitrate, you know that it doesn't dissolve. Whether if you got regular calcium nitrate, it would turn to soup in the bag. It immediately got a little humidity in it, it would just start dissolving. But they put wax around it to keep it from dissolving. That's why it doesn't turn to soup in the bag. So, you know, we've been using waxes, oils, natural fats, and as coatings on fertilizer for a long time, and mostly to keep them from dissolving too quickly. There are natural latex and resins that could be used, but what we're going to concentrate on today is our polymer coatings, or these are organic molecules that polymerize this, produce long chains or sheets that then cover the granule or prill. What has to be done to make a coating technology useful is it has to have some ability to remain around the granule or prill of the fertilizer. It has to be somewhat impermeable, but it can't be totally impermeable because then the fertilizer inside would never dissolve. So what they have done technology-wise is they've either taken impermeable coating and they've added additives to it to add wicks or pores so that it can allow some water in, or they produce a semi-permeable material like a membrane that allows, has pores that allows water in and diffusion out, but it still maintains the integrity or shape of the coating. The other thing that's important in coating technologies is whether or not it's going to swell. Swelling may not be a good thing. We'll talk about that in a little bit, why that could be a problem. So it shouldn't swell, and it should have enough strength. It should be resistant to damage, and that's been a problem with some of our coatings over the years. So one of the older technologies that's still being sold is sulfur-coated urea. Molten sulfur is sprayed as a coating or on or in a drum with your urea, so that it coats our urea in multiple layers or layers of sulfur. Then these sometimes has a wax layer put on top of that. So the breakdown or release from a sulfur-coated urea granule is both physical and then, of course, microbes reacting with the sulfur too. So it's it starts cracking. It starts as the water enters in through the cracks, and it starts to break down the coating. Then the size of the coating will determine its release pattern for sulfur-coated urea. Now, we don't really use this in agriculture. When it was first developed back in the 70s, late 60s and 70s, we all really thought this was where nitrogen technology was going to go. As it ended up, we never really did adopt this very wholeheartedly with field crops. And where it's remained today is within the turf industry. So we use a lot of sulfur-coated urea is used for turf use. 30–40% nitrogen depending on the coating. We have several of our turf fertilizer companies that make it now. It's generic, it's not under patent, so anybody can do this. You can open up a sulfur-coated urea plant if you would like. But it has fairly low cost, but again, it has had limited use in field crops. And the reason is because it's not, the release pattern's not that predictable. Generally, it lasts 8 to 12 weeks, but if you're in a cooler period of time, it's not going to break down as quickly, or you can have some that are released and some that aren't, some of the granules, so you can get streaking in turf. So they found in turf it's a better product for summer use, warm season. All right, so those are the old technologies still being used. As I said, that liquid formulation is probably where we use methylene ureas, triazones. Those are probably the most common things you in this room are going to be involved in if you're doing field crops. Again, if you're in a nursery or greenhouse or turf, you'll see some of those other products. All right, moving on to the next stage in coatings was the polymer coating era. This started in the 60s with that first material you see there, Osmocote, or the original Osmocote. And this technology is a thermoset resin. And what that means is you take two liquids, and then when they combine, eventually they harden to form the coating. Generally, they started using, one of the liquids they used was linseed oil. Nowadays, I think they're using soybean oil, and then they reacted it with another chemical that produced the polymer. And so, fairly, not that hard to do. They produce multiple layers around the prill. So again, Osmocote, the classic Osmocote, fall in this category. This was the first slow-release fertilizer really released in a encapsulated or coated product released, extensively used in the greenhouse and nursery industry. Anybody here use Osmocote? Yeah, all right, so anybody who's been in a nursery greenhouse at one time, you use Osmocote. Okay, the next technology that was developed was thermoplastic. Thermoplastic is you have a molten plastic, and then you take that molten plastic, you surround the particle, the granule or the prill of fertilizer, and then it hardens. The thing about these plastics is that they are plastic. They can be way too impermeable, so they have to add additives to them to allow wicks or channels or pores so that you can get water into the granule. A good example of that was Nutricoat, which was developed again in Japan. I use extensively again in the greenhouse nursery industry. I've been using Nutricoat for since the late 80s. And then reactive layer technology is the one that has brought coated products to you in the agronomic field. This is where you take in a drum or a reactive vessel, you spray two materials onto the prills or granules, and they produce a polyurethane shell. So, any of you used polyurethane lately? Any of you coated your deck or anything like that? That's polyurethane. So, you know what the material is. It produces a nice coating, and it will give you a good protection on a pretty thin layer. Doing some extra research last night, I found that this is often one of the preferred products for use in prophylactics. So that's a little, that's a trivia that you can take home tonight. I don't want to know. All right, but this is where your products like ES and the technology that they use. And how these coatings work is that shell has a permeability somewhat. There are some pores that allow water in. That water dissolves the fertilizer that's inside the granule, and it, because of osmotic conditions, it's higher concentration inside than outside. You're going to have the nutrients diffuse out into the soil solution. What the companies have done is they've taken they've developed the formulations that they use to produce the coating to give different release patterns. So whatever additives, the thickness of the coating, the additives they put into the coating material, and the size of the granule or prill that they start with, those all determine the release pattern. But it is temperature dependent. So these polymers, the diffusion rates through the pollen pores or the channels or wicks in the coating are controlled by temperature. They're not controlled by microbial activity. They're not controlled by moisture levels. So let's look at each one of these a little bit closer. The thermoset resins, or original Osmocote, were developed in the 1960s. And were the first commercialized. They have a multi-layered shell. Usually they're using a granule with a multi-nutrient granule. By the way, what's the difference between a granule and prill, you fertilizer people here?
Prill's liquid.
Yeah, a prill is dropped in the tower as a liquid form. As it drops, it produces that round. And it's usually it is one chemical formula. It doesn't have multiple types of fertilizer in it. So whatever you're dropping in that tower, whether it's a urea or potassium nitrate or whatever, it's going to be in that form as it drops. A granule, they grind up the fertilizers into a powder. They mix the different powders together, and then they put them into a granule and use materials to stick them together. And so that's how you get granular products. So that would be the difference as far as, does it matter which one you put a coat around? No, you can coat a crow, you can coat a grain, right? And they do. So these are used on complete or multi-nutrient fertilizers commonly. So if you look at the old Osmocote types, you'll see many different formulations depending upon what their use was in the greenhouse or nursery or crops they were growing, time of the year, where they wanted lower phosphorus, higher phosphorus, more ammonium, more nitrate sources. They would develop a granule with that and then coat it. Again, too costly. This was always too costly for field crops and too costly for vegetable crops. So it remained in the nursery industry. It did have a problem though. And the problem was that it had this, the way that it worked is, one of the things that happened is as the water entered into the granule, it started to swell. And oftentimes that swelling occurred so quickly that the coating would burst. And then you'd get dumping of what was inside. So you've just lost the slow release nature of the slow release fertilizer. So this premature release was an issue. And later versions of the Osmocotes, they solved this problem, but the original Osmocote had problems with its dumping. And if you dump a bunch of salts at one time, what do? You kill plants, or you burn plants, or you set them back. So this was an issue. Thermoplastic coatings developed in the probably the late 1970s, early 80s in Japan. You take a molten plastic and you coat the granular pearl with that. They've used them in multi-nutrient complete fertilizer formulations, widely adapted in our nursery and greenhouse industries. Trouble is, again, it's costly. This material costs more to, the thermoplastics cost more to use, so these products were always more costly. Good features is they did not swell, very resistant, can be blended, and they have really good predictable release patterns. So these NutriCoat, for example, made inroads into the nursery and greenhouse industry because they didn't have the problems that the old original Osmocote had. And so this was a solution to some of those problems with the earlier technologies. Trouble with these, again, they have to be done right. If you don't put the right additives in, you lock up the nutrients and you never release them. So you have to, the people who develop the coatings, they have to put additives in to develop those channels or ways to allow the nutrients, the water in and nutrients out. Well, the game changer for you and those of you in agronomy has been this, the reactive layer coating. This is where they take the two monomers as liquids, and as that those prills are rotating in the drum, they spray them on, and as they're spraying on, they're reacting to form that polyurethane shell. And by doing this, by just being able to spray them on and then reacting right in over top of the granule, they're able to develop a really thin layer and a strong layer. So this has brought the cost down to where it's more reasonable to use for field crop use. They don't swell. They have real thin coat sides, so the analysis is higher, 41 to 44, 45% nitrogen on urea, coated urea. They can be blended. You still have to take some care with them, but as long as you're careful, put them in at the last part of a blend, it works just fine, and they have really good predictable release patterns. So again, looking at ESN, which is one of the products that are out there, again, it's temperature to controlling diffusion and has an 80 to 90 day release at soil temperatures of 68 degrees. So they're able to have a good predictable release that would fit the crop, in this case corn. for use. Again, the companies that develop these coatings, they'll change the coating size, they'll change the formulation with different additives, they may change the pearl size. All these will dictate what the release pattern is going to be. One combined technology that you wouldn't think would have any market share, but it does, is this polymer sulfur coating, where they take a sulfur coat or urea particle and they put a very thin reactive polymer shell around it. That's thinner than the ones that are that we see as in the previous slide. So you get the benefits of both the polymer coat and the sulfur coat in these products. So what's the benefit of doing this rather than a regular coated urea, for example?
Stable.
A little bit more stable, yeah. Get a little sulfur. So, you know, I don't know where these really have a fit. They're used mostly, again, in turf applications right now. But again, another technology you'll see out there. All right, so who makes these? More people than I can list, but these are some of the players that are out there. Some of these are owned by the same companies, so they'll have the products that they bought from different companies over time. But Coden, Duration, ESN, Polyon would be examples of these polymer coated ureas that are being sold for production ag use. Horticulture examples, there are just loads and loads and loads of them out of there. Everest is the company that's bought a lot of these. They're part of ICL, another big company. They've got Osmocote, Polyes, AgriCoat, AgriMaster, Sierra Blend. So they offer a large group of multi-nutrient sources that are used in horticulture applications. They're trying to get into the agronomic and into vegetable crops right now. Scott's bought Osmocote and they still offer Osmocote. Florcan has the NutriCoat technology now also, so it's a company other than a Japanese company making it. ProCoats from Yara. So these are all examples of companies that are out there. If your company isn't up here, I'm sorry, but I can't keep track of all of you. So. Can you coat anything else? Sure, you give me a fertilizer, I'll coat it. Because these same technology, you can coat any fertilizer. So there are some that are commonly available. You can coat potassium sulfate. Any reason to coat potassium sulfate? For agronomic use? I can't think of any, but if maybe somebody in here could. You know, unless you have a soil that ties up potassium, has one of the clays that does, so I don't really see a great benefit to that. Coated potassium nitrate used in horticulture applications like vegetables, possibly a fit there. Coated calcium nitrate, again, in vegetable applications, probably some fits there. But you can coat anything. Folks that work with the greenhouse and nursery industries, they do a lot of coated complete fertilizers where they take a fertilizer granule that has multi-nutrient sources in it, and then they'll coat that. And there's literally dozens and dozens of formulations out there for the nursery and greenhouse industry, probably too many. You can, and actually some of these companies, if you are big enough, you go to them, they'll design whatever you want. You make whatever you want. These have some fit in vegetables and strawberry and certain fruits, very little fit in agronomic crops, way too costly. But this is what they're striving to do, is they're striving by their coating, both the nature of the coating, that's the chemical composition, the porosity, how thick it is, the type of chemicals that make up that shell, then the thickness of the granule. They use all those factors to deliver a certain release rate. There's two typical patterns that they've designed fertilizers with. One is a more linear release rate, This is for something that's growing, where you're maintaining something, maybe in a nursery application where you're trying to maintain growth, you're not getting large growth spikes with. The other is a sigmoidal one where you have a slow growth at the beginning and then a really quick growth period and then dropping off. So this is what they are designing these coats to give you for crops like corn, those things that would have that type of growth pattern. So annual crops fit very well the sigmoidal type. And so again, this is what the companies are striving to do. They will give you the technical data on these if you ask them. So what is the release rate? How much should be released at a certain time at a certain temperature? Remember, these all are temperature based, so if your temperatures are different than what they are testing, the release pattern is going to be different. So you have to really look at that, match that, work with their technology people to match your location. So I'm working with one of the companies now. In vegetables, what they need is my temperature data from, we're using this under black mass plastic mulch. You know, they need that temperature data to really design what we want for that particular crop. Some problems we've seen over the years, one is nutrient locking. This is where your coating is too thick, like with sulfur, so it never releases the nutrients, or you have too long a chain, you have urea formaldehyde, or somebody making a thermoplastic coating forgot to put in the right additives to make it porous enough or have the channels to get the fertilizer out. Anybody ever make a mistake in manufacturing? All right, so if you get a fertilizer slow release that doesn't seem to be working well, go back to the company and talk to them and see if there wasn't some issues in the manufacturing process. Because we've certainly seen this, the nutrient dumping. And this is where something happens to that coating that breaks the integrity of that coat, whether it's damaged, whether it's swelling and bursting, whether the coating was just not laid down properly. And then all the nutrients are released at once. And this has caused massive crop losses, particularly in the nursery industry. You see up there a $40 million award in Oregon for a company that offered these blends with a slow release fertilizer that dumped its nutrients. So this is a reality out there. So again, if you start working with these and you really want to work with a reputable company, get to understand their technology and make sure they have good quality control. All right, so why do you want to use these anyway? Because there's something else you can sell people, right? No. But the first reason is this whole idea of reducing nitrogen loss. So that's an environmental benefit. Enough research out there showing that you can reduce volatilization in certain crops where you're doing surface applications in a pasture or a hay situation, or small grains, or leaching losses. There are a lot of experiments that have done with that. So there are environmental benefits of using these. In fact, this is one of the reasons why they oftentimes are being promoted, is because there oftentimes is cost share money in different programs to have you offset the cost of using the slow release fertilizer. So something for you to look into. Is this something that there are cost share programs in your particular area? And of course, you know, these certainly, we've done research all throughout the Chesapeake watershed. It's shown benefits. Anybody here don't live in a sensitive watershed? All right. Just wanted to know. I want to move there. All right. The other is, can you reduce applications? So one of the things, one of the ideas was, since this is slow release, you can just put one application and you don't have to go back in the field for a second application or a third application. So could you eliminate a second top dressing in wheat? Could you eliminate a side dressing in corn? Or could you eliminate multiple fertigations in a vegetable crop? And the research is kind of unequivocal here. I mean, it's not always showing the ability to do this. We'll look at some of that in a little bit. How about reduced management costs? If you don't have to fertigate, because that reduces your management costs, or you don't have to have the additional equipment to do something like that. And one of the other benefits that has been seen on a lot of work is the idea is that you can actually reduce the nitrogen rate. So even though it costs you more, it may be 10 to 30% more to use these materials, or maybe as much as 50% more to use these materials. If you can use that much less of it and get an environmental benefit, you are doing good for the environment and having the same crop response. So we've certainly seen that. Again, it doesn't hold across all years. Why? Because some years are dry, and particularly on dry land situations. So in an irrigated situation, again, the research is kind of all over the board here. So what you're looking for is either increase in yield with the same fertilizer rate for this nitrogen efficiency with your slow release, with your controlled release, or maintaining the yield with a reduction in rate, or increasing the yield with a decrease in rate, or a large increase in yield with an increase in rate. All right, you have to do one of those things to make it pay. And they've looked at all these and a number of different crops throughout this region. Over the last 10 to 15 years, there's been dozens and dozens of research projects looking at these polymer coated products in field crops. We certainly have looked at them in vegetables. And then it boils down to economics. So again, one of those things that we saw previously has to occur so you have an economic benefit. And do we always see an economic benefit with controlled release fertilizers? And the answer is no. There's certain crops where it works better in, there's certain circumstances, certain soils, and certain seasons that it works where it works well. So this is just some, a slide from the ESN site, website, and showing that there is some benefit, and there is an economic benefit in using in this case, ESN. So the studies that are out there, there are not a lot of academic studies that really have done a good job of looking at the economics here. But I've laid out what you need to consider whether or not this is going to work for you. If you're getting government payments to help you, then you would add those on as part of the economic. All right, so in the end, you want what you're looking for in that controlled release fertilizer. Is it going to increase your nitrogen use efficiency, get more bang for your fertilizer buck? You apply less to the crop. You increase yield sometimes. You might eliminate the need for one or more additional trips across the field with fertilizer, and you reduce the environmental consequences of using that nitrogen. So some work just to give you illustrations over the last 10 to 15 years from some of our researchers. When Greg Pimford was here, you've probably seen this before, that in use in wheat, where you're putting that 30% with 70% of the soluble fertilizer, 30% of the ESN, controlled release, that's where you're getting your maximum yield. So you do save a trip across the field by doing that in wheat. On the other hand, they looked at putting ESN on many studies on about 5 years here in this region, whether or not you could eliminate side dressing by just putting putting ESN up front. And what does that show you there? Not really. So it's not something that works as well in corn to eliminate that need for side dressing. Certainly works. If you put all your fertilizer up front, the controlled release very much outperforms it, but nobody does that. So from an academic perspective, that's interesting, but people aren't putting all their fertilizer up front in corn. Other states have seen the same thing in wheat, where you've got a benefit of applying part of your nitrogen as ESN. This is from Kentucky on wetter soils, really seeing a good benefit here. So seems to have a really decent benefit in wheat. Not corn, that's a little more hard to justify. And part of the problem is it is a granular product. Is it easy to, as far as uniformity, and then the release pattern in corn, is it going to fit well enough to get the same benefit? And the answer is it doesn't always. Long Island, these are some slides from Sandy Menasha. She talked to her vegetable growers last year. Long Island has very sandy soils, gravel underlaying low organic matter. They're growing higher value crops, so she looked at potatoes and sweet corn. And what they found in their research is that you couldn't just use the controlled release. You had to have some soluble nitrogen in there. You don't want to go above 70 to 80% controlled release. And they were able to reduce their total nitrogen rates by up to 20%. So with potatoes, they looked at the timing, the release, where you had 60 to 80% of your nitrogen as slow release fit very well on the growth pattern of potatoes. You didn't get the losses where you had early precipitation events as far as leaching, and the yield results showed that they could go down to this 160 and get equivalent yields to their 200 rate with side dressing. So in this case with potatoes, it had an environmental benefit and it gave you equivalent yields, and in some cases better yields. They took this out and gave farmers the option to use their standard program, and then they put out these the controlled release fertilizer and the other program. And you can see, it's hard to see what's the writing on the bars, but in all cases, the grower standard program was somewhere between 20 to 40 pounds more nitrogen than the ESN. And what do you see there? It's giving equal yields, so that you can really drop down the rate of ESN and get you equal rates. So in essence, you were paying for the extra cost of that controlled release fertilizer in potatoes. Sweet corn, they saw a similar result here, is that they could reduce down the rate and get equivalent or better yields by having a portion of 60-80% of the nitrogen as the controlled release. So these were some of Sandy's recommendations. Small acres first, start with 10%. And then go from there, no more than 80% controlled release in the blend, and really had good benefits in wet springs. All right, about 15 cents more per unit in. All right, so in some work that we've done with this is from this past year in watermelons, some work that I just finished. Question was, could we replace our standard fertilizer program with a upfront application of slow release nitrogen? Again, would benefit by not having all that management time to fertigate, save the time involved in management of doing that. And the answer is no. In this case, we saw a reduction in yields of watermelons where we're using just a controlled release. This was all controlled release, so what we're going to have to do is what Sandy was recommending. We're going to have to put a little bit of soluble fertilizer up front to make this work. So that's something we'll move on to next year. Some older work that I did back 4 or 5 years ago, look at the zero rate here. These are all rates of compost, but the zero rate would be where we're just using fertilizers. In this case with zucchini, we saw no yield advantage to using the slow release. In fact, maybe a little bit of yield loss. Right. In watermelons, we also did not see an advantage to using slow release watermelons. So again, mimicking what we saw this past year. On the other hand, cantaloupes, we saw a little bit of an advantage. Again, look at the zero rate. We did see some advantage in peppers. We'll show you some more research on that in a little bit. And we did see on a second year where we used reduced rates of controlled release, pepper seemed to respond very well to using controlled release fertilizer. So it's a longer term crop. We're getting many more picks off of it over a longer period of time. So it probably, the release pattern fit that crop very well. And we were able to reduce down to 60% of the nitrogen by using controlled release compared to a standard program. Just another way of looking at it. So that CRF low, which has the highest bar, that was our highest yield. We looked at tomatoes. In this case, the 80% rate of controlled release nitrogen fertilizer gave us the best yields and may have been economically beneficial in